Hello again. In this video, we're going to go over section 2.6, part 4, which is on continuity. And specifically, we're going to look at Theorem 212, which has two parts to it. So the first part says if G is continuous at A and F is continuous at G of A, then the limit of F composed with G of X as X approaches A is simply the same as F evaluated at the limit of G of X as X approaches A. So in some sense, what this is saying is, as long as you satisfy these two conditions, you can move this limit past the function f and simply take the limit of g of x first as x approaches a, and then evaluate f at whatever that limit is. Okay, so I'm going to prove this. Let's prove this. Okay, so let's assume g is continuous at a and f is continuous at g of a, and we want to show that this limit, the limit of this composition as x approaches a, is the same as f evaluated at the limit of g of x as x approaches a. Okay, so let's start with this limit. And we're going to show that this limit is the same as this right-hand side. Okay, well, if g is continuous at a and f is continuous at g of a, by the previous theorem that we looked in the previous video, we know that this is equal to f evaluated at g of a. Now let me go back and just remind you of that theorem. That's the previous theorem, Theorem 211. Okay, so let's go back and look at that theorem real quick. So that was this theorem here. It said if g is continuous at a and f is continuous at g of a, then the composition function f composed with g is also continuous at a. Now, if f composed with g is continuous at a, then by the definition of continuity, this limit as x approaches a of this composition is the same as f evaluated at g of a. Okay, so that's where we're getting this. Okay, so we know those are equal, right, by this theorem, Theorem 211. Okay, so knowing that, we also know that g is continuous at a, right? So if g is continuous at a, then by the definition of continuity, then we know the limit of g of x as x approaches a is the same as g evaluated at a. And that's the very definition of continuity at a. So those must be equal. And so I can go back up to here and replace that, right? We know what this is equal to. F of g of a, right, is the same as f evaluated at this limit of g of x as x approaches a, because it is g of a. They're equal. So long as g is continuous at a, okay? And so that proves it. The limit of this composition as x approaches a is the same as the limit of g of x as x approaches a, evaluated, where f is evaluated at what that limit is. Okay, so basically, again, what this theorem is telling us is as long as you satisfy both of those conditions, you can actually find the limit of g of x first here and figure out what that limit is, and then take the function and evaluate it at that number. And that'll be the same as finding the limit of this composition of f and g as x approaches a. Okay, so that proves that theorem. All right, let's actually apply the theorem now. Okay, so I'm going to look at part A in example 5. We're going to find the limit of this square root function as x gets closer to -1. Okay, now this is a composition of two functions, so let's write it out. Let's find f and g. Okay, g is going to be the inner function, which is 2x squared minus 1, and then f of x will be the outer function, which is the square root of x. Okay, now we're going to evaluate this limit using the previous theorem that we just talked about, Theorem 212. And so we're going to attempt to evaluate this limit by finding the limit of the inner function first, and then taking the square root of that limit. Okay, but can I do that? Right? I would like to know if these are equal, right? The square root of this limit. Is that the same as the limit of this composition, right? Are these equal? Well, by the previous theorem, these are equal so long as g is continuous at a. So let's check. Is g continuous at a, where a is -1? Okay. So that's kind of something we have to show to use the theorem. So is g continuous at a? Well, sure. This is a polynomial, right? This is a second-degree polynomial. Polynomials are continuous everywhere. So in particular, this polynomial would be continuous at -1. So yes. Okay. And then f of x needs to be continuous at g of a. Okay, in other words, g of -1, right? And g of -1, let's see what that is. When you plug -1 into g right here, -1 squared is 1, and then you get 2 times 1, so 2 minus 1 is 1, right? All right, so is this function continuous at 1? And the answer is yes. This square root function is continuous at 1. I mean, one argument is if you look at the graph of square root of x, it looks like this. And at x equals 1, you can see that the function is continuous at 1. Okay, so yes, this is continuous at 1. Right, f of x is continuous at 1. Okay, so we've satisfied both of the conditions of theorem. These are the two conditions for theorem 212. And so we are, by theorem 212, these are equal. Okay, this limit can go past this square root function, and you can actually find the limit of the inner function first and then take the square root of it, as long as you satisfy both of those conditions. Okay. Okay. So now all we have to do is find the limit of this function 2x squared minus 1 as x gets closer to -1. Well, the good news is this is a polynomial function, and so we can evaluate this by direct substitution. Okay, so I'm just going to plug -1 into there, and when you plug -1 into there, you just get 2 times 1 minus 1, which is 1. Okay, so we know this limit's equal to 1 by direct substitution. And so then you get the square root of 1, which is 1. Okay, and so now we know the limit of this composition. Okay, so that's a good application of the first part. We're actually using part 1 of that theorem, the first part of the theorem. All right, now we're going to go back and look at the second part of that theorem. Okay, so the second part of theorem 212 says that if the limit of g of x as x approaches a is equal to L, and f is continuous at L, then the limit of this composition as x approaches a is the same as f evaluated at the limit of g of x as x approaches a. Okay, so notice you're getting the same result here. In other words, the limit of this composition, you can actually move the limit past f and take the limit of g of x first, and then evaluate the function at that limit, which is the same result as this. The conditions are different though. Notice up here, g needs to be continuous at a, but down here, we only need the limit of g of x as x approaches a to be equal to a number L. Now remember, if g is continuous at a, then the limit of g of x as x approaches a is actually g evaluated at a. But what this says is we don't even need it to be g of a. We just need it to equal some number L, not necessarily g evaluated at a. So it loosens this condition here. This is kind of a stronger condition. This one's a bit looser. Okay? This limit does not have to necessarily be equal to g of a like it is up here. It just needs to be equal to some number L. Okay? And then the second condition here, right, f is continuous at g of a, is now f needs to be continuous at this number L. And as long as you satisfy both those conditions, you get the same result that you did up here in part 1. Okay, so this is actually a looser condition here. Okay, this is a more abstract case. Okay, so this is actually a stronger, more useful part of the theorem. Okay. Okay, and the reason it's more useful is because we don't necessarily have to make sure that this limit here is actually g evaluated at a. We just need it to equal any number L, not necessarily g evaluated at a. So that makes it more useful, right? It applies to more situations. Okay, so let's apply that part of the theorem. Okay, so we're going to find this limit here. Okay, so we're going to find the limit of this cosine function as x gets closer to 2. Now notice this is a composition of two functions, right? So let's write it out as a composition. So let's say the inner function g of x is the x squared minus 4 over x minus 2. And the outer function f would be cosine of x. Okay, so if you say f composed with g, you'll get this cosine of x squared minus 4 over x minus 2. Now, in order to, we're going to appeal to that theorem 212, part 2 now. And again, anytime you apply a theorem, make sure you satisfy the conditions. In this case, there's two conditions. The first condition is that the limit of g of x as x approaches a, so in this case 2, we need to make sure that this limit is equal to some number, L. It needs to be a finite number. Okay, so let's see if it is. Okay, well, you might attempt to use direct substitution here because this is a rational function, but notice that when you plug a 2 in, you get 0 over 0, so you have an indeterminate form. And that theorem that mentioned that we can use direct substitution for rational functions also mentions that we can do that as long as the denominator is not 0 when we use direct substitution. But that's not true here, right? When I plug a 2 into the bottom, I get 0. Okay, so, but remember, when you get the form 0 over 0 like this, what you do is you try to rewrite it in a determinable form. So I think what you can do here is factor. This top piece factors into x minus 2, x plus 2. Okay, and you can see the x minus 2's cancel out, and so this limit is the same as the limit of x plus 2 as x approaches 2, which happens to be 4 by direct substitution. Okay, so this is equal to a finite number. So we've satisfied this first condition. Okay, now the second condition is that this limit, that the function let's go back and look at it. I think it has to exist, right? Let's see. So, oh, it has to be continuous, right? F needs to be continuous at L, right? So that's the second condition. Okay, so F needs to be continuous at this point here, right? So let's see if that's true. Well, look, this is a cosine function, right? Cosine function, if you graph it, oscillates between 1 and minus 1. So something like this. And I think you can see intuitively it's continuous at every point. Okay, so in particular, it's continuous at 4. Okay, so certainly f of x is continuous at 4. Okay, so we've satisfied both conditions of the theorem, right, where this is L. Okay, and since we satisfied both conditions of the theorem, we can now make the conclusion that this limit can be written, right, this limit can go past the cosine. So you can find the limit of the inner function first, and then take the cosine of that limit. Okay, and we already know this limit. We found it. The limit as x approaches 2 of this function happens to be 4, and so the answer would be cosine of 4. Okay, so we're able to find this limit using the second part of Theorem 212. Now, one thing I want to mention is we couldn't have used the first part of Theorem 212. And the reason we couldn't have used the first part of Theorem 212 is because the condition, this first condition for the first part of Theorem 212, okay, that first part said it had a stricter requirement. It said that this limit had to be equal to g evaluated at a. Or, well, I mean, technically it says g of x needs to be continuous at a. But that means this limit, by definition of continuity, right, at a point, this means that this limit is equal to g of a, right? So notice up here, this limit right here as of g of x as x approaches 2 is equal to 4, but g of 2, let's see what g of 2 is. If you plug a 2 into g, right, you get 0 over 0, right, which is undefined. Okay, so this first condition wouldn't have been satisfied if you had tried to appeal to the first part of Theorem 212, because this limit over here is not equal to g of a, because g of a is undefined. Right, g of 2, really, in this case, because a is 2. Okay, so there's no way these could be equal. This is not even a number. All right, this has to be some number, and it has to equal this limit. And this is not even a number, so there's no way they're equal. So you couldn't appeal to the first part of Theorem 212, right? But you can use the second part of Theorem 212 because this is not necessarily g of a, right? This is not g of 2, but it is some finite number, okay? And so that's why the second part of Theorem 212 applies to more cases. Okay. So I hope you found this video helpful. Thank you for watching. Bye-bye.